In this video, we are comparing two frameworks to look at the world, Newtonian versus Lagrangian mechanics. Even though both are correct in the sense that they predict the same trajectory of dynamical systems, they are founded on fundamentally different perspectives on reality. Before diving into the details by solving an example using both frameworks, a brief overview. Newton famously came up with the concept of forces acting at a distance as mediators of cause and effect. To predict how an object will move, we first identify all of the forces acting on it. Then, adding them together to find the net force, we retrieve Newton's second law, which states that the second time derivative of the position through time, or the acceleration, times the mass is equal to the net force acting on the object. And note that a dot above a symbol is shorthand notation for the time derivative, and thus x double dot is equal to the acceleration. Lagrange, on the other hand, thought of space as filled with fields, propagating the effect of a source to a distant object. Much like on the surface of water, the source can be a disturbance, for instance a stone thrown in, whose effects then spread out and affects different objects in the water. The resulting framework from this perspective to predict an object's motion first has us calculate the kinetic and potential energy, here written as T and V. Subtracting them from each other, we obtain the central quantity, called the Lagrangian. Then the equivalent of Newton's second law is the Euler-Lagrange equation of motion. And exactly how this equation is derived I will leave for another video. However different these points of view seem to be, they actually result in exactly the same predictions when it comes to dynamical systems. And to see them in action, let's describe the motion of a simple pendulum. A mass m is suspended by a string of length L and is able to swing back and forth. To solve this dynamical system means to put its motion into a function such that we can describe where the mass will be at any moment in the future. Concretely, this means finding a function, theta of t, that describes how the angle changes with time. First, we will solve this system by using the familiar method of Newton's second law, which is all about forces. In fact, the first step is to identify all of the forces acting on this object, and then adding them together to find the net force. Then we use this net force to fill in Newton's second law, which links the net force with the acceleration and thus the motion of our object. And then we remind ourselves that Newton's second law is actually a vector equation. And indeed, in this case, we have two-dimensional motion. In fact, if we simply draw the Cartesian axis, an x and a y axis, then we see that when the pendulum swings back and forth, the x and the y component will change through time. Therefore, this single Newton's equation will result in two separate equations of motion, one for the x direction and one for the y direction. However, there is a neat little trick that we can use to reduce these two separate equations in two dimensions to just one equation of motion, and thereby reducing our two-dimensional motion to just one dimension. To do this, we first realize that even though our object can indeed move in two dimensions, its motion is heavily restrained. Because the string with which it is attached has a fixed length L, the object will only be able to move on a segment of a circle with radius L. Therefore, instead of describing the motion as a change in both the x and the y direction, we can do so by using just one parameter, namely the change in distance that the object travels along this circle segment. And this parameter is called s of t. Changing to this perspective basically means that we're changing coordinate axis. Instead of using the Cartesian coordinates x and y, we are using the coordinate system attached to this circle. We have the tangential direction, which at each point is tangent to the circle, and we have the radial direction, which points radially inward. This means that instead of the directions x and y, we have the directions r and t. And since we're only interested in the motion along the tangential direction, we can drop any dynamics in the r direction, and thus we are left with one equation. Therefore, Newton's second law now reduces to just one dimension, we have the net force in the tangential direction, which is equal to the mass of the object multiplied by the acceleration of our object, again in the tangential direction. And since the acceleration is simply the second time derivative of the displacement, we can write that this is equal to m times s double dot of t. Therefore, what we are left to do now is to find the net force in the tangential direction. This means to find the tangential components of each of the forces separately. First, for the tangent force, this is quite trivial, because it is pointing in the radial direction, towards the center of the circle, and therefore the tangential component of this vector is equal to 0. Then, to find the tangential component of the force of gravity, we will have to do some geometry. Concretely, what we need to find is an expression for the projection of this vector force onto the tangential direction, as shown here. If we extend the radial direction and look at the angle between this direction and the force of gravity pointing down, we see that this angle will be exactly the same as the angle our pendulum makes with the vertical direction. Then, if we consider the fact that the radial direction and the tangential direction are perpendicular to each other, meaning an angle of 90 degrees, we see that the angle of projection that we need is 90 degrees minus theta. Now that we have this angle, we can very easily write down the tangential component, namely just the magnitude of the force of gravity, Fg, multiplied by the cosine of 90 degrees minus theta. And of course a minus sign in front of it, because it points in the opposite direction of the tangential base vector. The magnitude of the force of gravity is simply m times g, and the cosine of 90 degrees minus a specific angle is simply the sine of this angle. And because only the force of gravity has a tangential component, this is immediately the net force in the tangent direction, and we can directly write down Newton's second equation, namely that minus m times g times the sine of theta of t is equal to m times s double dot of t. Now we see that we have two functions of t here, both describing the motion of the pendulum, the angle theta and the displacement s. However, we would like to have a solution with only one of them, and in particular this angle theta and how it changes with time. Because this displacement is on the segment of a circle, we can very easily write this distance as a function of the corresponding angle. S is equal to L, the radius of the circle, multiplied by the corresponding angle theta. Using this, we can rewrite this equation. Apart from cancelling the mass on both sides of the equality sign, we can rewrite this s double dot as L times theta double dot, since L doesn't change with time. Then, if we isolate theta double dot on one side of the equality sign, we get the following equation, which is an important intermediate result of using Newton's method. And later we will see that the Lagrangian method will indeed yield the exact same equation of motion. Let's now solve this equation once and see whether we indeed get an intuitive result. And to do so, the first step is to realize that this is a differential equation, meaning that we need to find a function of t instead of just a value x in a normal algebraic equation. Now, unfortunately, this specific equation does not allow you to find this function theta of t using analytical methods or just pen and paper. To make some progress, however, we can do this small angle approximation, where the sine of theta is approximately equal to theta, if this angle is very small. Making this approximation, we get a simplified equation. And this equation basically tells you to find a function of t that if you take the time derivative twice, or the second derivative to time, you will get the same function again, but just with a constant factor in front of it. Now, I won't go into the details of how to solve this equation. I will do that in another video. However, I will briefly cover the result. We see that the function theta of t, so how the angle of the pendulum changes with time, is simply equal to a harmonic oscillator with an amplitude equal to the starting angle theta 0. Because indeed, if we put t to 0, so our initial condition, the cosine becomes 1, and we have indeed theta 0. And this will be the final result of Newton's method. We indeed find what we expected. Let's now move on and compare this with the Lagrangian method, where we're going to study the same system, but forget everything we know about forces. The first step here is to find the expression for the kinetic and potential energy of our system. For the kinetic energy, we know that this is equal to 1/2 times the mass times the velocity squared. Now the trick here is of course to find an expression for this v, the velocity. Now if we again use the coordinates of the radial direction and the tangential direction, then we know that our velocity will always be in the tangential direction. Moreover, if we again use the displacement along this circle segment as our displacement, then we conclude that the velocity is simply the time derivative of this s of t. And therefore we get that the kinetic energy is equal to 1/2 times m times s dot squared of t. However, again, we want to write this as a function of this angle theta of t, for which we can again use the same formula that this circle segment, s, is equal to the radius of the circle, L in this case, multiplied by the angle theta. Filling this in, we ultimately get that the kinetic energy is equal to 1/2 times m times L squared times theta dot squared. Then we move on to the potential energy, for which we know that in a gravitational field, this will be equal to m times g times h. And in this specific case, we will use h as the distance between the ceiling and the mass of the pendulum. Now this might seem odd, because normally we choose h to be the distance from the ground, but since the potential energy is a relative quantity, we can use the 0 point wherever we like. And does it make sense to choose it such that our future calculations will be simplified? Now, using simple geometry, we know that this h can be written as L times the cosine of theta. And this gives us a very neat and compact expression for the potential energy. In the second step, we are going to construct the Lagrangian, which is simply the difference between the kinetic energy and the potential energy. Having found the expressions for both of these terms, we can easily construct the Lagrangian. Now note that this Lagrangian is a function of the variable that we're interested in, theta, and its time derivative, theta dot. And again with theta being a function of t, describing the motion of this pendulum. The third and final step is to write down the Euler-Lagrange equations of motion, which is basically the analogon of Newton's second law. It says that the time derivative of the partial derivative of the Lagrangian to theta dot is equal to the partial derivative of the Lagrangian to theta. And now that we have all of these expressions, we can simply fill in this equation and see what we get. For the left-hand side of this equation, we see that we need to take the partial derivative of the Lagrangian to theta dot. And we see that theta dot only occurs in the kinetic part of the Lagrangian, namely theta dot squared. So we can easily fill this in and then take the time derivative. Ultimately, we get that the left-hand side is equal to m times L squared times theta double dot of t, since m and L are constant through time. Now the right-hand side of the equation of motion is even simpler. We simply have to derive the Lagrangian to theta. And in this case, theta only occurs in the potential term of the Lagrangian. So we simply derive this and get m times g times L times the sine of theta, which is a function of t. Then we bring both of these together to equate the left-hand side to the right-hand side again. We see that we can cancel out the mass, which is a good sign, and we can also cancel out 1 power of L. Then by isolating this theta double dot, we again get a differential equation for theta of t. And in particular, this is exactly the same differential equation that we got from using Newton's method. And if we have the same differential equation, we will get the same result. So we don't even need to solve this differential equation just to know that we will indeed get the same result, a harmonic oscillation with the initial angle theta 0 as its amplitude. And therefore we see that both of these approaches yield the same result, even though they are based on fundamentally different perspectives of how reality works. And this brings us to the end of this video. If you learned something, give it a thumbs up, and I will see you in the next one.